Hello people from the future, welcome to Normalized Nerd. In this video, I'm gonna be talking about DBSCAN algorithm. It's an unsupervised learning algorithm for clustering. First of all, I'm gonna explain every conceptual detail of this algorithm and then I'm gonna show you how you can code DBSCAN algorithm using Scikit-Learn. If you are new to my channel, then please subscribe to my channel and hit the bell icon. I make videos about machine learning and data science regularly. So let's get started. First of all, let me tell you the full name of this algorithm. Well, it's a big one. It is density-based spatial clustering of applications with noise. Well, there are three particular words that we need to focus on from the name that are density, clustering, and noise. From the name, it's clear that the algorithm uses density to cluster the data points, and it has something to do with the noise. Maybe it can identify the noise very well. We will see later. First of all, let us understand what is density. Well, from the physics we know that density is just the amount of matter present in a unit volume. Well, we can easily extend this idea of volume into higher dimensions or even in lower dimension. Okay, so for example, we have this region here, okay, and we have some data points in this region, and we have another region of same area, and we have got these many data points here. So from the idea of density, obviously the density of first region is greater than the second region because there are more data points, more matter in the first region, okay, and DBSCAN actually uses this concept of density to cluster the dataset. Now, to understand the DBSCAN algorithm clearly, we first need to know two very important parameters. The first one is epsilon, and it is actually a measure of neighborhood. Well, what is a neighborhood? Well, suppose this is our point that we are considering right now, and let me draw a circle around this point, making this as a center and at a distance epsilon. So we are gonna say this circle as this point's neighborhood, okay? So epsilon is just a number which represents the radius of the circle around a particular point that we are gonna consider the neighborhood of that point, okay? And the second parameter is mean sample. And by the way, I'm going to represent min samples as Z throughout my video because it is convenient for me. But if you're going to study this DBSCAN from the internet, then probably you're going to encounter this term mean samples. So just keep that in mind, okay? And this is actually a threshold on the least number of points that we want to see in a point's neighborhood. Suppose we are taking Z is equal to 2. And in this point's neighborhood we have actually 2 points, this point itself and this point. So this point actually passes the threshold z equal to 2, and let us focus on this point. And suppose this is our neighborhood of this circle. I know it's not a perfect circle, but please bear with me. And here you can see that we have got 4 points in this neighborhood, 1 2 3 4. So this point also satisfies this threshold z equal to 2. Now if I said z equal to 3, then this point won't satisfy this because we have got only 2 points in its neighborhood, but this point will satisfy it because we have got more than 3 points, okay? Now, based on these two parameters, we are first gonna classify every point in our dataset into 3 categories. The first one is core points, second one is boundary points, and the third one is noise. Let us see the core points first, okay? So this is a core point. Why? Well, if I say this point is core point, then it must satisfy one condition. The condition is number of neighbors. must be greater than or equal to our threshold, min samples, or z. Okay, so if I set z equal to 3, then this point actually satisfies this condition. So we say this is one core point. Now let us see other core points in this dataset. Okay, so we have got this core point, this core point, this core point, and these 3 points are also core points. But remember, this point, and this point are not core points. Okay, now let us see the second type of points, that is boundary points. Okay, so if I say one point is boundary point, then it has to satisfy 2 conditions. The first condition is number of neighbors must be less than z, and the second condition is the point should be in the neighborhood of a core point. Okay, for example, this point has actually less than 3 neighbors in its neighborhood, but it is in the neighborhood of another core point, so this point is actually a boundary point. And same thing goes for this point also. So we have got 2 boundary points in this dataset. Okay, now let's see the last kind of point, that is the noise point. Well, this definition is very simple: neither core point nor boundary point. So this point is neither a core point nor a boundary point, so we say this point is a noise point. Okay, so we have classified every single data point into 3 categories. So the first step of our DBSCAN algorithm is actually done. Congratulations. Now you need to understand another concept. Suppose we have got 2 core points here. Well, I'm not drawing the neighborhood points, but remember that this is x and this is y, and they both are core points. Okay, so if x and y are neighbors, then we join them by an edge that we call as density edge. Okay, now let's see 4 points here, 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 and here, and assume that every point is a core point, and say this is point A and this is point B. Assume they are connected via density edges. Let me name this also. So you can see C is in the neighborhood of A, D is in the neighborhood of C, B is in the neighborhood of D, but A and B are not neighbors. So if this kind of situation arises when 2 core points are connected via density edges, then we say A and B are density connected points. Okay, A and B are density connected points. Now let me write the rest of the steps of this algorithm. So our first step is actually done, which was to classify the points. Second step is to discard noise. So we are going to discard this point. Okay, and the third step is assign cluster to a core point. For example, I am taking this core point and assigning it a cluster red. Okay, and the fourth step says color all the density connected points of a core point. Okay, so we have to color all the density connected points to this point the same color red. Okay, so by following this, we have to color this and this. Remember, we are not gonna color this and this just now because boundary points can never be a part of density connected point. Only core points can be density connected. Okay. Now our algorithm says repeat this two steps for every uncolored core points. So here I'm gonna take this core point first and I'm coloring this a new color, that is I'm assigning a new cluster to it, cluster blue, and we have to assign all the density connected points the same cluster. So these 3 points will belong to the blue cluster. Now comes the fifth step, which is by the way the last step. It says that color boundary points according to nearest core point. So if you just look at our example, then you will see that we have two boundary points here, and for both of the boundary points, the nearest core point belongs to the red cluster. So we have to assign the boundary points also red. And voila, the DBSCAN algorithm is done. Let me explain a couple of very important points about this algorithm. Well, the first point that I want to say is how to determine epsilon and z. Well, to be honest, this is a difficult question because the DBSCAN algorithm is very sensitive to its initial parameters. So if you change this epsilon and z even slightly, then your algorithm can actually produce very different results. So that is one downside of this algorithm. But you can choose them wisely if you have the proper domain knowledge. As a rule of thumb, if you have a large number of examples, then you can choose Z in the order of your dimensionality. So if you are working with a 10-dimensional data, then it is preferable to choose a value of Z close to 10, like 12, 15, like that. Okay. Now to know the value of epsilon, here's a thing you can try. Suppose you have chosen z equal to 5. So after that, what will you do? You will just find the distance of fifth neighbor from every data point. So you will have a distance array, and the ith entry in that array will represent the distance of fifth neighbor of ith data point. And then you are gonna sort this distance array and you are gonna plot it like this. In the y-axis, you will just have the distance, and in the x-axis, you will have the index. That is simply the I, okay? So ideally, you should get a graph like this. As we have sorted this, so as the index will increase, the distance of the fifth data point from that point will also increase. So if your luck favors, then you can find this elbow type of thing and you can just cut it by a horizontal line, and the horizontal line will cut the y-axis at some point, and you can just take this value as your epsilon. But obviously in real world you might not get this smooth elbow, but this is a trick that can be applied in some cases. Okay, now let me come to the second important point. Very effective in noise elimination. As you saw in my previous example, we were classifying the points into 3 categories, and there was a category of noise points. So this algorithm can be applied in noise datasets very well. And the last point is DBSCAN can't handle higher dimensional data very well? Well, this is actually a fault of many clustering algorithms, as I have talked in my k-means video also. As the dimensionality increases, we have to look into a larger volume to find the same number of neighbors. So the similarity between the points decrease, and that will result in clustering errors. So I guess that was a pretty decent explanation of DBSCAN algorithm, and now let's jump into the code section. First of all, I'm gonna make a fake dataset. And if you have watched my previous video on k-means clustering, then you will find that I am using the same method of producing fake data points. So it will be really helpful if you just go and watch my k-means video too after this video. In this way, you will actually learn two clustering algorithms at once. Isn't it awesome? So please go and check that out too. Okay, so to make the fake dataset, we are using our favorite library Scikit-Learn, and we need to import the function called make blobs from sklearn.datasets. Okay, and this function takes these arguments. The first one is n samples. Well, this just represents how many data points we need to produce, and the second argument is centers. This tells us that how many clusters will be there, and the third argument is n features. Well, this is just the dimensionality of our dataset. Here I am choosing 2 because two-dimensional datasets are really easy to represent visually, okay? And if you want to produce the exact same results that of mine, then you can actually use random state argument and set it to 20, okay? And this function will actually return two things. The first thing is the data points that I am assigning to the variable x, and the second thing it's going to return is the array of labels. Now remember that DBSCAN is an unsupervised learning, so we don't provide the labels, that is the ground truths, at the beginning. We let our algorithm find those labels on its own. So I have left it blank with an underscore, okay? And we need some other libraries like pandas, matplotlib, and numpy, okay? So moving on with the visualization. So you can clearly see that we have got three clusters here, 1, 2, and 3. And now our DBSCAN algorithm will try to find the labels on its own, okay? And the DBSCAN algorithm is really simple to implement in Python using Scikit-Learn, because the Scikit-Learn library has already implemented this for us. We just need to import this class from sklearn.cluster module, okay? So the class name is DBSCAN, and we need to create an object out of it. The object that I have created here is named as clustering, and we need to input the two most important parameters that I have discussed in the conceptual portion, and the first one is epsilon EPS, and the second one is z, or min samples. Now look here that I have given epsilon as 1 and min samples as 5. As I have told earlier that this total depends on the domain knowledge, so please choose them wisely. And like every other algorithm in scikit-learn, we need to use the dot fit method on our training set x, and then we are just getting the labels, okay, labels of the clusters. So it will give us an array, and to see how many clusters has it found on the dataset, we can just convert this array into a set, and we just print the length of the set. Now you can see that here is 4, but what happened? We saw that our dataset contains 3 clusters. Wait, the first cluster, that is the -1 level cluster, is actually represents the noise in this DBSCAN. So you can see, if we just visualize our clusters by this simple piece of code, then we will find something like this. And you can see that these 2 points, first point and second point, I don't know if you can see this clearly, but you can just see the legends here. So -1 label corresponds to the noise. So even though we have got 4 clusters here, the first cluster actually represents the noises, so we discard them. And if we just look at the other points, you can clearly see that our algorithm has found 3 clusters. blue cluster, yellow cluster, and green cluster. So that's how easy it is to implement DBSCAN using Scikit-Learn. I hope that you found this video helpful, and please share this video and subscribe to my channel. And if you want to suggest a new topic that I should make a video on, then please comment in the comment section. Stay safe. Thanks for watching.